Light is often seen as predictable, smooth, and controllable. We use lasers to cut with precision, transmit data through fiber optics, and illuminate microscopes with perfect focus. But under certain extreme conditions, light behaves wildly, generating patterns that are unstable, self-interacting, and completely unpredictable. This strange behavior, known as nonlinear optical chaos, challenges our usual understanding of how light should act and reveals a surprising link between optics and chaos theory. So what causes this chaotic behavior in light? The answer lies in how materials respond when exposed to very intense light, usually from powerful lasers. In normal situations, light passes through a material and the response is proportional to the intensity. Double the light, double the response. But in nonlinear optics, things change. When light is strong enough, the material's response becomes nonlinear. Small increases in light intensity can cause massive changes in behavior. Light can bend itself, mix with itself, or even create new colors. And in certain conditions, this can lead to patterns that shift, split, or pulse unpredictably over time. Can light really become chaotic like weather or a dripping faucet? Yes, and not just in theory. In experiments with nonlinear optical fibers, lasers passing through special crystals, or even in optical cavities, mirrors facing each other, scientists have observed chaotic pulses, spiral patterns, and flickering spots of light. These effects depend on tiny changes in input intensity, beam alignment, or temperature, making the output sensitive to initial conditions, just like the chaos found in weather systems or turbulence in fluids. One striking example involves a setup called a nonlinear ring laser, where a beam of light travels in a loop through a nonlinear medium. At certain power levels, instead of producing a steady beam, the system starts generating irregular, pulsing bursts of light that never repeat in the same way. These are not errors. They're an intrinsic part of how the system evolves. Even more intriguingly, these chaotic light patterns can be mapped and analyzed using the same tools developed for studying brainwaves, stock markets, or planetary orbits. Why does this matter? Because chaotic optical systems are not just unstable, they're rich in information. Researchers have explored using optical chaos for secure communication, where a message is hidden in the seemingly random pulse of a chaotic laser. Others are looking at chaotic lasers for neuromorphic computing, mimicking the unpredictable but patterned activity of biological neurons. In photonic circuits, nonlinear chaos could be harnessed for complex signal generation or ultra-sensitive sensors. But chaos also poses challenges. In high-powered laser systems used for medical procedures, manufacturing, or telecommunications, uncontrolled chaos can introduce noise, instability, and even damage. This has led engineers to develop chaos control techniques such as feedback loops or engineered materials that suppress chaotic modes and stabilize the beam. Oh, can intense light generate unpredictable patterns? Absolutely. And these patterns are more than just visual curiosities. They represent a fascinating frontier where optics meets nonlinear dynamics, offering both technical challenges and creative opportunities. When light becomes chaotic, it becomes a medium not just of clarity and order, but of complexity and emergent behavior, reminding us that even the most familiar forces in nature can surprise us when pushed to their limits. In media, with a Kerr nonlinearity, the refractive index increases with light intensity, causing the center of the beam to advance more rapidly than its edges. This leads to an intensity-dependent phase shift that can focus the beam inward, narrowing it until a dynamic balance is struck between diffraction spreading and nonlinear self-focusing. When the input power exceeds a critical threshold, this balance collapses and the beam may undergo filamentation or catastrophic collapse, giving rise to spatial chaos. Tiny variations in the input beam profile or intensity become amplified during propagation, leading to spontaneous formation of filaments with unpredictable spacing and shape. Femtosecond laser pulses propagating in glass can break into multiple filaments with irregular spacing and intensity, like a river splitting into random rapids when water pressure becomes too high. A continuous wave beam propagating through a nonlinear medium can undergo modulational instability, where small fluctuations in amplitude or phase grow exponentially and disrupt uniformity. The result is the fragmentation of a smooth beam into a train of pulses or spatial filaments, with their characteristics depending delicately on the input power and background noise. In regimes where nonlinearities dominate, these pulse trains behave chaotically, merging, splitting, and changing shape in ways that defy prediction. Continuous infrared light in a nonlinear fiber, for instance, can evolve into a chaotic sequence of high-intensity spikes, much like ripples on a pond spontaneously clustering into erratic formations under a steady breeze. Stabilizing optical solitons, which are pulses stabilized by a balance between dispersion and nonlinearity, can also be sources of chaos when they interact. In systems where two or more solitons collide within a cavity or fiber, the delicate balance breaks down, producing irregular fluctuations in amplitude and pulse timing. These perturbations feed back into the gain medium, amplifying noise and destabilizing pulse trains. In mode lock lasers, this manifests as an abrupt transition from steady clock-like pulses to chaotic bursts, triggered by seemingly trivial changes like a small tweak to the diode current. It is like a convoy of cars driving at even intervals, suddenly bunching and scattering chaotically when the road conditions change just slightly. IQ optical microresonators, especially those that support whispering gallery modes, confine light with great efficiency. However, when strongly pumped, they may support multiple competing modes. Nonlinear coupling among these modes gives rise to irregular, unpredictable energy transfer and sudden jumps between resonance conditions. The system becomes highly sensitive to minor changes in pump power or temperature, which can produce erratic spectral shifts and chaotic frequency comb lines. A silicon microdisc resonator under intense continuous wave pumping can jump unpredictably between modes, yielding a noisy output like a chain of pendulums swinging rhythmically until pushed too hard and descending into chaotic independent motion. Ultra-short pulses traveling through long optical fibers experience a complex interaction of dispersion, self-phase modulation, four-wave mixing, and Raman scattering. Together, these effects generate broad, noisy output spectra where the temporal and spectral features fluctuate shot to shot. The resulting field exhibits spatio-temporal chaos, where subpulses form, distort, and vanish in a pattern reminiscent of turbulent flow. In photonic crystal fibers pumped with femtosecond lasers, the supercontinuum output becomes highly variable and difficult to control. Like a lightning storm scattering flashes unpredictably across the sky with each new cloud formation. When optical feedback is introduced to a laser by reflecting part of the output back into the cavity after a delay, the result is often chaotic modulation of both amplitude and phase. The time delay interferes with the internal laser dynamics, creating irregular pulsations and broadening the spectral output. The structure of the chaos depends on the delay time and feedback strength, and while such systems are useful for studying nonlinear dynamics and encryption technologies, uncontrolled feedback severely compromises beam quality. A diode laser with moderate optical feedback from a mirror may exhibit erratic spikes instead of a smooth output, like hearing your own voice echoed back repeatedly until it generates an unpredictable screeching feedback loop. Photorefractive crystals, which change refractive index in response to light-induced charge redistribution, can also support optical chaos. When multiple laser beams interfere within these media, dynamic gratings form and evolve, introducing feedback loops that destabilize the beam structure. As the refractive index changes slowly over time, the system develops memory, further amplifying its sensitivity to beam alignment and intensity. In barium titanate crystals, this manifests as slowly shifting, chaotic speckle patterns that seem to pulse with randomness, like sand dunes constantly reshaped by gusts of wind into unpredictable forms. Nonlinear optical microresonators generating frequency combs can shift from stable, evenly spaced spectral lines to erratic, chaotic patterns under certain conditions. Variations in pump detuning or power levels destabilize the comb, introducing irregular spacing and line intensities that are unsuitable for metrology but valuable for applications needing high entropy. Silica microresonators. Near resonance can exhibit sudden transitions between a clean comb and a noisy broadband output with only milliwatt scale shifts in pump power, much like a finely tuned choir falling into noisy disarray when the conductor loses rhythm. Harnessing the unpredictability of optical chaos provides powerful tools for random number generation, a critical need in cryptography and statistical computing. Chaotic light sources generate noise that, when sampled above the electronic noise floor, can yield high-speed streams of random bits. These optical random number generators surpass traditional electronic methods in entropy quality and throughput. Careful system design ensures that the chaos is genuine and not contaminated by low-dimensional or periodic behavior. A vertical cavity surface emitting laser operating in a chaotic regime can deliver gigabit per second bit streams that pass stringent randomness tests, like stirring cream into coffee and taking droplets from the swirls. Each one unique, each one unrepeatable.